Hello, geometry. Check mic 1 2. What's good? Now, right? It's asking for your last name, first name, all that jazz. Today we're looking at the 6.3 notes. So let's go ahead and transition into that. Yeah, we're looking at Unit 6, Lesson 3. We're talking specifically about triangles that are 45, 45, 90. So, consider a square of side length equal to 1. All right, so here's this side, and let me do a color that stands out a bit more. Here's this side, right? And here's this side, right? They're all 1, 1, 1, right? Side lengths of 1. And we're drawing in a diagonal. All right. We're drawing in a diagonal. What is the length of that diagonal? Let's do L for length. Well, we know that this is a right triangle because, of course, all four corners of a square are right angles. So this is a right triangle. And what did we just do in the previous video? We used the Pythagorean theorem. We know that we can use the Pythagorean theorem. So let's do that. So the square root of 1 squared plus 1 squared, right? Because we're trying to find the hypotenuse. So the square root of leg squared plus leg squared. So that's the square root of 2. So L is root 2 long. What are the measures of the angles in the triangle that we formed? So we know, of course, that one's 90, and then this is 45, and this is 45. Hence it being a 45. Hence this topic being 45, 45, 90. And why are those 45? Because this diagonal is splitting the 90 degrees in half. 90 divided by 2 is 45. So our measures are 45, 45, 90. So every isosceles triangle, every right isosceles triangle is a dilation of one another. So I can take this simple little triangle that's 1, 1, root 2, and I could blow it up and take something that's 1, 1, root 2 and maybe multiply it by 3, and then it becomes 3, 3, 3 root 2, or like that. Or I could blow it up even more and it becomes 7, 7, 7 root 2. But it's always following that same pattern, right? Because when you dilate, everything stays the same proportion-wise, okay? So on this triangle over here, we're going to write generically K for scale factor. Every right isosceles triangle, in other words, every 45, 45, 90 triangle, takes the following form. It will always be, the legs are always the same length. We're calling them K long, and then the hypotenuse is always K times root 2. Every single time. Every single time, okay? So we're just going to use that pattern on repeat here. Are you ready? Because after 6 in a row, you ought to have it down. So the legs are the same, right? Those are K. And then we multiply by root 2. Multiply by root 2 to get the hypotenuse. So therefore, the hypotenuse is 5 root 2. You see how it's following the pattern? Let's see it again. This leg is 8 long. So if that leg is 8 long, then the other leg has to be 8 long, right? The legs are the same length. And if both legs are 8, then multiply by root 2. Oops. I'm just going to do, I'll do an x, right? Multiply by root 2, and you get 8 root 2 for y. You see how it's following that pattern? The legs are the same, and then you multiply by root 2. The legs are the same, and then you multiply by root 2. Here, in this example C, we were given the hypotenuse. It's 9 root 2. So following that pattern, let's make this the first question of the video. What does that mean both of these legs have to be? If the hypotenuse is 9 root 2, then each of the legs must be... Each of the legs are 9. Hopefully that's what you just answered. And I hope you really see that pattern, right? Legs are the same, 5, 5, 5 root 2. 8, 8, 8 root 2. 9, 9, 9 root 2. All right, let's spice it up though. What if the hypotenuse is a whole number? What if the hypotenuse doesn't have a root 2 in it? Does that mean we've just broken the system? No, it does not. It does not mean we broke the system. It just means that k is not a whole number. That's all that means. K is not just simply 3 or 4. It's something weird, right? So the hypotenuse is always k root 2. So let's solve for k. Hypotenuse is always k root 2. So let's solve for k. Divide by root 2. So k equals 19 over root 2. If you remember from the last video, we don't like square roots in the denominator. So let's multiply by root 2 over root 2. And that becomes 19 root 2 over 2. And that is k. So the legs are a weird length, not the hypotenuse. Where here the legs were whole numbers and the hypotenuse had the root 2, this one's the other way around. So x is 19 root 2 over 2, and so is y. It's still following the same pattern, though. It's still following the same pattern. Because what is the pattern? The legs are the same, which they are. They're just not a whole number. Okay? It's just not a whole number. And the hypotenuse is instead. Seeing another one will help you. So here, they gave us the leg. So in a 45, 45, 90 triangle, the legs are always the same. Right? Compare it to either one of these problems up here. Right? We said this is 5, well then that's 5. We said this is 8, well then that's 8. We're making the same conclusion here. If this is 9 root 2, then this is 9 root 2. And then how did I get to the hypotenuse? We multiplied by root 2, right? Well, guess what? I'm going to do the same thing. Multiply by root 2. But when you do that, when you take 9 root 2 and multiply it by root 2 times root 2 cancels out the radical, and it becomes 9 times 2, which is 18. Voila, x is 18. So it's still following the same pattern. It's just that k is a weird number and by weird I mean it has a radical, right? I hope you see how it's following the same pattern though, right? Legs are the same, multiply by root 2. Legs are the same, multiply by root 2. Legs are the same, multiply by root 2. We're doing the same step. So, here's another question then. What is x? Okay. You should have just had what I just said in your mind. Legs are the same. So immediately, you should have said x is root 10. The legs are the same. All right. What was I just repeating? Legs are the same and we? Okay. We multiply by root 2. Can you do that for me? Back-to-back questions here. Can you do that for me? Solve for y. So when you multiply by root 2, root 10 times root 2 is the square root of 20. You combine the insides, which simplifies to be 4 root 5. Or sorry, 2 root 5. Do you remember how to simplify? You find the biggest perfect square. This is 4 times 5. 4 is a perfect square. What's the square root of 4? 2, and then the 5 is left over. 2 root 5. Okay, so we saw that pattern on repeat here, right? You're going to have a lot of classwork problems that are just doing that pattern over and over and over. Get that Let that sink into your head. Legs are the same, multiply by root 2. Or the other way around, if you start out with the hypotenuse, you can simply divide away the root 2 and you get the legs, which is what we did here. You see how we divided by root 2 to get the legs? So if you're given the legs, you multiply by root 2. If you're given the hypotenuse, then you divide by root 2 to solve for the legs. Should I write that down? Given a leg, multiply by root 2 to get hypotenuse. Given hypotenuse, divide by root 2 to get the leg. Sorry, that looks sloppy, but I said that kind of slow, so hopefully you were able to write that down. Okay, so knowing that every 45, 45, 90 triangle follows this pattern, let's see if something interesting happens to sine, cosine, and tangent. If every 45, 45, 90 triangle follows that pattern, is there some sort of pattern that shows up when it comes to sine and cosine? The answer, yes, there is a pattern. Let's find out what that pattern is. So if this is the hypotenuse, divide away the root 2. That one's easy. When you divide away the root 2, oh, the legs are both 3. So AB is 3 and AC is 3. And it says to find sine of B. Here's B. So this is opposite, adjacent, hypotenuse. Okay? Opposite, adjacent, hypotenuse. You know what I didn't mention in the video, I don't think, and I'll say it now. I really wish I would have mentioned it in the video. That's crazy that I didn't mention it. SOHCAHTOA. It's a fake word, but it's pronounceable. SOHCAHTOA. Sine is opposite over hypotenuse. So 3 over 3 root 2 is sine. Guess what? We don't like radicals. We can cancel the 3's though, and we're left with 1 over root 2, and then we multiply by root 2, and we end up with root 2 over 2, right? A radical times itself cancels out the radical. That's why we do this, because it gets rid of the radical. Cosine of B, well, the adjacent and opposite are the same, so cosine of B is also the same thing, right? I'm not going to show that work, right? I don't need to do that twice, do I? And then, so ka being adjacent over hypotenuse, and then toa, opposite over adjacent. So 3 over 3, which comes out to be 1. So if we look at it the other way around, here's C, and now this has become, the opposite, and this has become the adjacent. Well, it doesn't matter that they switch, right? Because the numbers were the same. So I'm just going to end up getting the same answer. You realize that, right? I can do it. I can do this one, though, right? Just so I can help you realize that, right? Opposite, oh, that's still 3 over hypotenuse. That's still 3 over 3 root 2, right? The problem's not changing here. So guess what? Voila, we end up with the same thing. Adjacent is still 3. Hypotenuse is still 3 root 2, and we end up with the same thing. And despite the fact that opposite and adjacent switched, because the legs are the same here, 3 over 3, no matter how you look at it, comes out to be 1. Right? Let's look at another one. We're given a leg. So what's the other leg? 5. And what does that make the hypotenuse? 5 root 2. So sine of B, well, here's B. 5 is the opposite. 5 is the opposite. And 5 is adjacent, and this is our hypotenuse. So let's see how this compares. Let's see how this compares to what we were doing above. When we do opposite, that's 5. And when we do adjacent, hypotenuse, that's 5 root 2. The 5's cancel, and look at that. We end up with 1 over root 2 again. The same thing is happening. It's just that 5's are canceling instead of 3's. And we end up with root 2 over 2. And adjacent is the same number, so guess what? The same thing is going to happen. We end up with root 2 over 2. And then instead of doing 3 over 3, as we did here, opposite over adjacent, we're going to get 5 over 5. But we still end up with the same answer. And these are going to be the same as well. I hope this is really I hope at this point you're like, okay, I get how switching these things around, it doesn't matter. Everything's canceling the same way. So we end up with root 2 over 2, root 2 over 2, and 1. So we've seen 1, 2, 3, 4 things in a row here. It doesn't matter what size the triangle is. It doesn't matter what the numbers are. It doesn't matter how you look at it. Sine of 45 degrees is always going to be root 2 over 2. That is just a fact. And cosine is always going to be root 2 over 2. And tangent is always going to be 1. If you take Algebra 2, if you take pre-calculus, or if you take calculus in college or something like that, I can guarantee you're going to be memorizing these numbers. If you can memorize these 3 things, it's just going to make life easier instead of having to always look it up. These are just numbers that show up time and time again. That's why we're really staring at it here. Okay? That's why we're really staring at it here. So, sine of 45 degrees, no matter where, no matter what triangle, no matter how big, no matter how small, if you have a 45-degree angle, it's always, always, always going to end up with the same result. Okay? Root 2 over 2. And, I realize I didn't ask too many questions. Is there one other question I can think of at the end here? Here's a question. Why are these the same? Why are those two the same? It makes sense that sine of 45 degrees, this is an open-ended question. I'm going to talk a little bit more and then I'll prompt the question. It makes sense that sine of 45 always stays the same. But why do these match? There's a very specific answer that is like the perfect answer, but you might say something that's generally correct. Why is it that these two are the same? What is it about the triangle that makes sine and cosine the same? Open-ended question there, and we're under 20 minutes. Thank you, and I'll see you in the next one.